The sun has long since disappeared behind the horizon, leaving only the softest glow painting the western sky in shades of lavender and deep rose. You stand at the threshold between two worlds, the familiar world of roads and buildings behind. You and ahead, stretching endlessly into the gathering dusk. An ocean of sand that seems to breathe with the rhythm of eternity itself. Your feet sink slightly into the cool grains at the desert's edge, and immediately you feel something profound shift within you. The sand beneath your toes isn't just ground. To walk upon, it's a library, a vast collection of stories written in a language older than words. Each grain that now cradles your weight has traveled further than most people ever will, carrying within its crystalline structure the memory of mountains that once stood proud against ancient skies. The desert spreads before you like a frozen sea, its dunes rising and falling in waves that seem to pulse with their own slow heartbeat. In the growing twilight, these formations take on an almost liquid quality, as if the entire landscape might begin flowing if you watched long enough. And perhaps, in ways your human eyes cannot perceive, it already is. You breathe deeply, and the air carries scents that speak of vast distances, the clean, mineral smell of stone worn smooth by millennia of wind, the faint metallic tang of iron oxides that paint some sands red as rust, and underneath it all, something indefinable that might be the scent of time itself. This is air that has traveled across continents, gathering stories from every landscape it has touched. As your eyes adjust to the desert's subtle beauty, you begin to notice that what seemed like uniformity from a distance reveals itself as infinite complexity up close. The sand is not simply tan or beige, but contains multitudes grains of quartz that catch the last light like tiny stars, dark fragments of volcanic glass that whisper of explosive births, smooth pieces of feldspar that once formed the heart of granite mountains, and countless other minerals, each with its own tale of creation and transformation. You kneel and let a handful of sand pour through your fingers, watching as each grain catches what light remains. In this simple gesture, you're holding the remnants of mountains that stood when dinosaurs walked the earth, feeling fragments of rocks that once lay at the bottom of ancient seas, touching particles that have been shaped by forces so patient and persistent that they make human urgency seem like the flutter of a hummingbird's wing. The science of what you're experiencing begins to unfold like a gentle revelation. These grains didn't appear here by magic. They are the children of erosion, the offspring of a process so slow and thorough that it can reduce the mightiest peaks to fine powder given enough time. Water, ice, and wind have been the artists here, sculpting and refining each particle through countless cycles of freezing and thawing, wetting and drying, heating and cooling. Some of the sand in your palm may have started its journey as part of the Rocky Mountains, broken free by frost that split rock along invisible weaknesses, then carried by streams that have long since changed course or disappeared entirely. Other grains might have begun their travels in the Appalachians, worn smooth by rivers that meandered through landscapes that existed before grass evolved to cover the earth. The wind stirs around you now, not with any urgency, but with the patient persistence that has shaped every contour of this desert. It lifts individual grains and carries them just far enough to begin their next chapter, adding infinitesimally small changes to dune faces that will, over years and decades, completely transform the landscape's appearance. You're witnessing sculpture in its slowest, most meditative form. As you stand, brushing the sand from your hands, you notice how quiet the desert has become. But this isn't the empty silence of absence. It's the full silence of presence, of a landscape so vast and patient that it makes space for every small sound to be heard clearly. The whisper of sand shifting in the evening breeze becomes audible, a sound like distant rain or the turning of ancient pages. This quietude allows your other senses to expand and sharpen. You become aware of the temperature differential as the Air begins to cool more rapidly than the sand, creating gentle currents that stir around your ankles. You notice how the lack of vegetation changes the way sound travels, how voices would carry further here, and how the absence of the usual background hum of modern life allows you to hear subtleties, normally masked by civilization's constant chatter. The desert's memory isn't just geological, it's climatic. The sand beneath your feet remembers when this region was covered by shallow seas, when massive glaciers locked up so much of the world's water that sea levels dropped, and ancient rivers carved new channels through exposed continental shelves. It remembers tropical periods when forests grew where now only the hardiest plants survive, and ice ages when the patterns of precipitation shifted so dramatically that entire ecosystems migrated like slow waves across the continents. Looking up at the stars beginning to emerge in the darkening sky, you realize that the desert offers something increasingly rare in our illuminated world: true darkness, the kind that allows the full majesty of the cosmos to reveal itself. Here, far from light pollution, the night sky becomes a dome of infinite depth, and you understand that you're not just standing on the Earth's surface, but on a planet spinning through space, carrying its cargo of sand and stone and all the stories they contain. The temperature continues to drop, demonstrating one of the desert's most distinctive characteristics: its dramatic daily temperature swings. Without the moderating influence of large bodies of water or dense vegetation, the desert's thin, dry air cannot hold heat the way humid environments do. The same clear skies that allow the sun to beat down mercilessly during the day now allow that accumulated heat to radiate back into space with equal efficiency. You pull your jacket closer and marvel at this natural demonstration of basic physics. How? The specific heat capacity of dry air and the lack of water vapor to trap outgoing long-wave radiation combine to create these extreme temperature fluctuations. It's a landscape of extremes, but extremes that follow perfectly predictable physical laws. As you begin to walk deeper into the desert, each step reveals new textures underfoot. Sometimes your feet encounter areas where the sand has been packed and smoothed by wind into surfaces as firm as pavement. Other times, you sink into loose, deep sand that flows around your ankles like cool water. These variations aren't random. They reflect the complex relationship between wind speed, grain size, and moisture content that governs how sand behaves and settles. The dunes ahead of you rise like sleeping giants, their forms both alien and oddly familiar. There's something about their curves that echoes the lines of waves frozen in time, or clouds made solid. This isn't coincidence. Both sand dunes and ocean waves are governed by similar physical principles, shaped by fluid dynamics, whether that fluid is air or water. The approaching night brings with it a sense of anticipation, as if the desert is preparing to reveal secrets that only emerge in darkness. You can feel the day's heat still radiating from the sand beneath your feet, creating subtle updrafts that will soon begin to move individual grains in ways that daylight hours, with their more dramatic thermal differences, do not allow. Each grain of sand around you is a time capsule, and the desert itself is a vast archive of Earth's history. The feldspar fragments speak of granitic intrusions that cooled slowly deep within the crust. The quartz grains carry memories of beach sands from Paleozoic shorelines. The dark minerals tell stories of volcanic eruptions that painted ancient skies with ash and transformed sunsets for months across entire continents. But the desert remembers more than just geological time. It also holds the memory of every wind that has ever blown across its surface. The orientation of ripples in the sand, the steep faces and gentle slopes of the dunes, the patterns of erosion and deposition, all preserve information about wind direction, speed, and seasonality with remarkable precision. Standing here in the growing darkness, surrounded by this vast library of deep time, you begin to understand that you're not just visiting a landscape, You're entering into a conversation with the planet itself, learning to read the language that Earth uses to tell its own story. The desert whispers its memories in frequencies too low for human ears to detect directly, but your feet can feel the subtle vibrations. Your skin can sense the thermal signatures, and your mind can begin to decode the visual patterns that preserve eons of climate data. The stars are fully visible now, and their light illuminates the dunes with a silvery glow that makes the entire landscape seem to shimmer with an inner radiance. You realize that some of the minerals in the sand around you are actually fluorescent, containing trace elements that would glow with ethereal colors if illuminated by ultraviolet light. Even in darkness, the desert holds hidden luminescence. As you continue walking, your footsteps joining the eternal conversation between wind and sand, you find yourself wondering about the stories held not just in the grains beneath your feet, but in each individual particle. If you could somehow decode their complete history, you would have access to a record of Earth's changes more detailed and extensive than any human chronicle. The wind picks up slightly, and you can hear it beginning to work its ancient magic on the dune faces ahead. Somewhere in that gentle susurrus lies the key to understanding how simple grains of mineral matter can be organized by nothing more than moving air into structures of breathtaking beauty and complexity. The desert is preparing to teach you its most fundamental lesson, that even the most basic materials, given enough time and the right conditions, can be sculpted into forms that rival any human art. And as you walk deeper into this vast classroom of sand and stone and starlight, you find yourself beginning to listen more carefully to what each grain might be trying to tell you about the secret language it carries within its crystalline heart. You kneel beside the shore where countless grains gather like a library of whispered stories, each one smaller than a thought, yet carrying the weight of millennia. Your fingers sink into this granular ocean, and you begin to understand that you are touching not just sand, but time itself, crystallized moments from distant peaks, ancient riverbeds, and forgotten coastlines that have traveled impossible distances to rest here beside you. Each grain beneath your palm speaks in its own subtle language, a vocabulary written in crystal faces and weathered edges. The quartz grains catch moonlight and hold it briefly, like tiny lanterns, remembering their birth deep within cooling magma chambers, where they first learned to organize silicon and oxygen into perfect geometric patterns. They whisper of the moment they crystallized, when molten rock slowed its dance and allowed these microscopic architects to build their flawless structures, atom by atom, following blueprints written in the fundamental forces of chemistry. Lift a handful and let the grains cascade between your fingers, feeling their individual weights and textures, each one a unique messenger from a different geological story. Some are angular and sharp, recently broken from their parent rocks by frost and storm, still carrying the jagged memory of sudden separation. Others are rounded and smooth, polished by countless miles of river tumbling or endless seasons of wave action, their edges worn gentle by the patient persistence of water and wind. Not the feldspar grains tell different tales, their pinkish and cream-colored faces speaking of deep continental roots, of granite batholiths that cooled slowly beneath ancient mountain ranges. They remember the weight of miles of overlying rock, the gradual cooling that allowed their crystals to grow large and strong, and then the long, patient work of erosion that finally freed them from their igneous prison and sent them wandering across the landscape. As you run your fingers through this granular constellation, you begin to perceive the subtle percussion orchestra that plays whenever grains encounter one another. Each collision creates vibrations, tiny sound waves that travel through the pile of sand like whispered conversations. The larger grains produce deeper tones when they strike together, while the finest particles create higher frequencies, an almost musical scale determined by size and density and the physics of elastic collision. Scientists have learned to listen to this granular music using sensitive instruments to decode the frequencies that emerge when sand moves and settles. They discover that different types of grains produce different acoustic signatures, like fingerprints written in sound waves. Quartz sings differently than feldspar, and both sound distinct from the darker notes of magnetite or the bright chimes of shell fragments. The sand is literally singing its composition, telling anyone who knows how to listen exactly what stones and shells and coral reefs contributed to this gathered chorus. You press your ear closer to the sand and imagine you can hear these microscopic symphonies, the constant quiet percussion of grain against grain as wind shifts. The surface layers and waves rearrange the shoreline architecture. Each breeze creates cascading avalanches of individual particles, and each avalanche generates its own acoustic pattern, a brief musical phrase in the ongoing composition that this beach has been performing for thousands of years. The concept of angle of repose becomes poetry as you watch how the grains naturally arrange themselves. When you scoop up sand and core it out, it doesn't spread randomly, but forms predictable slopes, each grain finding its place according to invisible rules written in the physics of friction and gravity. The angle depends on the grain's shapes and sizes, their surface textures and moisture content, creating natural sculptures that follow mathematical principles while appearing entirely organic and flowing. You notice how water changes everything about the sand's behavior and voice. Dry grains flow like liquid, shifting and sliding with fluid grace, but add just a little moisture, and they begin to stick together, forming temporary architectures that can support the weight of sandcastles and footprints. The water molecules create tiny bridges between grains, surface tension acting like microscopic glue that holds the structure together until the moisture evaporates and returns the sand to its flowing, individual state. The waves arrive and retreat in endless rhythm, and with each cycle, they sort and resort the grains according to their unique properties. Heavier minerals sink deeper while lighter particles remain near the surface. The largest grains gather where the wave energy is strongest, while the finest particles settle in calmer waters or get carried far offshore to rest in deeper, quieter places. This hydraulic sorting creates natural gradients of size and composition that you can feel beneath your feet as you walk along the water's edge. The sand changes character with each step, sometimes coarser, sometimes finer, creating a textural map of wave energy and water flow patterns that shift with tides and seasons and storms. You begin to understand that each grain carries within its crystalline structure a record of its journey through deep time. The internal arrangement of atoms reflects the conditions present during its formation, the temperature and pressure and chemical environment that existed when this particular piece of matter first organized itself into its current form. Geologists can read these atomic archives like pages in an ancient book, decoding the thermal histories and chemical signatures that reveal where and when each grain began its long migration. Some grains traveled here from nearby cliffs and headlands, their journey measured in decades or centuries as they tumbled down stream beds and rolled along sandy floors. Others have wandered much farther, carried by ancient rivers from mountain ranges hundreds of miles inland, or transported by wind systems that lifted them from distant deserts and carried them across continents before depositing them here at this particular convergence of land and sea. The most well-traveled grains may have made multiple journeys, eroded from one rock formation, deposited in another, then eroded again and transported to yet another location in endless cycles of breakdown and reconsolidation. They are the most seasoned travelers in Earth's geological recycling system, each one a veteran of multiple rock cycles, carrying chemical and textural evidence of every environment they've encountered. You scoop up another handful and hold it close to your face, marveling at the diversity contained in this seemingly uniform substance. Under magnification, each grain would reveal its own unique character, its crystal faces and inclusion patterns, its trace element signature and isotopic composition, all the microscopic details that make it individually distinct despite its participation in this vast collective of similar particles. The realization dawns that you are holding a piece of Earth's continuous conversation with itself, a physical manifestation of the planet's ongoing process of self-transformation. The mountains that gave birth to these grains continue to rise and erode. The rivers that transported them continue to flow and change course. The waves that sort and shape them continue their eternal dialogue with the shore. This sand represents both destruction and creation, the breakdown of ancient solid structures, and their reorganization into new temporary arrangements. It embodies impermanence and continuity simultaneously, each grain both ancient and constantly renewed through its participation in Earth's dynamic systems. As you let the final grains slip through your fingers, you sense that you've been holding not just sand, but a tangible piece of the planet's memory, a physical archive of geological time that connects this quiet moment to the vast, slow dance of continental drift, mountain building, and the patient work of wind and water in reshaping the surface of the world. The grains settle back into their temporary resting place, rejoining the vast congregation of particles that will continue their journeys long after you've walked away. Some destined to travel farther down the coast, others to be swept offshore into deeper waters. All of them participants in stories that began millions of years ago and will continue for millions more. Standing here surrounded by these countless tiny messengers from Earth's past, you begin to wonder about the larger patterns they create. The way individual grains organize themselves into dunes and beaches and barriers, following rules that seem to emerge from the collective behavior of innumerable small parts working together, without any central planning or conscious design, are walking now through a landscape that seems to pulse with its own quiet life. The sand beneath your feet shifts and settles with each step, and as the last light of day fades into the gentle embrace of evening, you begin to notice something extraordinary. The dunes around you are not the silent, static monuments you once imagined them to be. They are breathing. Listen closely, and you will hear it, the soft, almost imperceptible rhythm that matches the rise and fall of your own chest. The wind moves across the curved faces of these sandy giants, and they respond like living lungs, expanding and contracting in a dance as old as the earth itself. Each grain of sand is a tiny participant in this vast respiratory system, shifting and settling in patterns that follow laws both ancient and precise. The science of this breathing is beautiful in its simplicity. As wind flows over a dune's windward slope, it creates a zone of low pressure on the leeward side, drawing air through the spaces between sand grains. The dune literally inhales through its porous body, pulling wind deep into its sandy core. Then, as pressure equalizes, it exhales through countless microscopic channels, releasing that same wind in gentle sighs that you can feel against your skin if you pause and pay attention. But tonight, as you continue your journey through this breathing landscape, you discover something even more wondrous. These dunes do not simply breathe, they sing. The first note reaches your ears like a whisper from the earth itself. It is low and resonant, a bass note that seems to emerge from the very foundations of the dune beside you. You stop walking and tilt your head, wondering if you imagined it. But there it is again, a deep, throaty hum that vibrates through the soles of your feet and up into your bones. This is the voice of the singing dune, and each one has its own unique song. The dune before you, with its steep avalanche face and precise slope angle of 34 degrees, produces this particular low frequency through a phenomenon that scientists call acoustic emission. As billions of sand grains cascade down its face in tiny avalanches, they create friction grain against grain, layer against layer, and this friction generates sound waves that resonate through the entire dune structure. Imagine, if you will, The dune is a massive natural organ pipe. The sand grains are not random particles, but carefully sorted musicians, each one the perfect size and shape to contribute to the symphony. Years of wind have sorted these grains with the precision of a master craftsman, removing the too large and too small particles, leaving behind only those that are just right, typically between 0.1 and 0.5 millimeters in diameter. Smooth and rounded by countless journeys across the desert floor, you place your hand against the dune's flank and feel the vibration directly. The sound travels through the sand at about 150 meters per second, much slower than sound through air, creating a rich, complex tone that seems to emanate from everywhere and nowhere at once. The frequency depends on the grain size. Smaller grains create higher pitches, larger ones produce deeper tones. This particular dune, with its medium-sized grains, hums at about 105 hertz, a note that falls somewhere between a low A-flat and G on a piano dot. As you walk along the base of this musical mountain, the song changes. Different sections of the dune face have slightly different grain compositions, different moisture levels, different compaction densities. Each variation creates its own harmonic, its own voice in the choir. The result is not a single pure tone, but a complex chord that shifts and evolves with each gust of wind, each small avalanche, each footstep you take in the sand. Other dunes in the distance contribute their own voices to this desert symphony. A smaller dune to your left produces a higher, more crystalline tone, perhaps 450 hertz, like a flute singing in the darkness. Its grains are finer, more uniform, and they create friction at a different frequency. The sound carries across the still night air, mixing with the deeper tones of larger dunes to create harmonies that no human composer could have imagined. The mechanics of this sand music involve forces and interactions that occur at scales both microscopic and massive. At the grain level, each particle of sand has been shaped by wind and time into an almost perfectly spherical form. When these spheres roll over and against each other during an avalanche, they create what physicists call stick-slip motion. They stick together momentarily due to surface tension and electrostatic forces, then slip suddenly as gravity overcomes friction. This sudden release of tension creates a tiny vibration, and when billions of grains undergo this same stick-slip motion in synchrony, their individual vibrations combine and amplify into the singing sound you hear. The dune acts as a resonating chamber, much like the body of a violin or the tube of a trumpet. The sand's internal structure, the way grains are packed together, the tiny air spaces between them, the moisture content that acts like a conductor, all contribute to how the sound waves travel and amplify. The dune's shape itself determines which frequencies will resonate most strongly, creating the particular pitch and timbre of its song. You climb carefully up the gentler windward slope of the humming dune, each step causing small cascades of sand that add their own tiny notes to the ongoing symphony. As you rise higher, the sound changes around you. You are now inside the instrument, and you can hear layers of music that were invisible from below. There are overtones and undertones, harmonics that flutter and dance around the fundamental frequency like butterflies around a flower dot at the crest. You pause to catch your breath and survey this landscape of living music. The view reveals dunes, stretching to every horizon, each one a potential voice in nature's choir. Some are actively singing, their steep faces catching just the right amount of wind to trigger their acoustic emissions. Others rest in temporary silence, waiting for the right conditions, the right wind speed, the right humidity, the right disturbance, to add their voices to the night's performance. The relationship between wind and sand music is delicate and precise. Too little wind, and there is insufficient energy to trigger the avalanches that create sound. Too much wind, and the turbulence disrupts the organized grain motion needed for resonance. The singing typically occurs when wind speeds reach between 5 and 20 kilometers per hour, a gentle to moderate breeze that provides just enough energy without overwhelming the system. Humidity plays its own crucial role in this acoustic ecosystem. Dry sand grains move more freely against each other, creating cleaner, more resonant tones. When moisture increases, it acts like a lubricant between grains, dampening their vibrations and muffling their song. This is why the singing is often clearest in the evening and early morning hours, when humidity is lowest and the sand has had time to dry from the day's heat. You sit now on the dune's crest, feeling the gentle vibration beneath you as the sand continues its quiet song. The sound seems to sync with your heartbeat, or perhaps your heartbeat has adjusted to match the rhythm of the earth. This is bioacoustics in its most primal form. The resonance between your body and the landscape, a reminder that you too are made of minerals and matter, shaped by the same forces that created these singing mountains. The pitch of the dune's song tells a story of its composition and history. The uniformity of grain size speaks of long journeys, countless cycles of erosion and deposition that have sorted and refined the sand over thousands of years. The clarity of the tone reveals the purity of the material quartz grains, worn smooth by wind, free from the clay particles and organic matter that would muddy the acoustic waters. As you listen more carefully, you begin to distinguish the different voices within the dune's song. There are the fundamental tones created by the primary avalanche phases, but layered over these are subtle harmonics generated by smaller slip events, micro-avalanches that occur continuously as the wind reshapes the surface. Some frequencies seem to pulse rhythmically, created by the interaction between wind gusts and the dune's natural oscillation patterns. The temperature of the sand also influences its voice. Cooler evening sand is denser, more tightly packed, creating different resonance characteristics than the looser, expanded sand of midday heat. As the night progresses and the sand continues to cool, the pitch subtly shifts. The timbre becomes richer, more complex. You are witnessing hearing the daily vocal exercises of a geological instrument that has been practicing its scales for millennia. Other creatures in this desert landscape have learned to tune into these sandy frequencies. Certain insects and small mammals use the sound as a navigation aid, the way sailors once used lighthouse beacons. Birds flying overhead can detect the infrasonic components of dune songs, frequencies below human hearing that carry for vast distances through the still desert air. The singing dunes speak in a language older than human civilization, a vocabulary of frequencies and harmonics that connects them to similar formations around the world. In the Gobi Desert, the Sahara, the dunes of Nevada, and Peru, wherever the right conditions exist, the earth raises its voice in these ancient songs. Each location has its own dialect, its own acoustic signature determined by local geology, climate, and the particular history of wind patterns that shape the sand. You close your eyes and let the sound wash over you completely. The dune song seems to bypass your ears and resonate directly in your chest cavity, as if your body has become part of the instrument. This is the power of low-frequency sound. It doesn't just reach your eardrums, but penetrates your entire being, creating a physical sensation of connection with the landscape around you. The mechanism behind this physical resonance involves the way sound waves interact with the fluid-filled spaces in your body, your chest cavity, your sinuses, even the chambers of your heart can act as resonating chambers for certain frequencies. When the dune sings at just the right pitch, your body responds sympathetically, vibrating in harmony with the earth beneath you. As you prepare to continue your nighttime journey, you notice that the wind is beginning to shift. The dune's song changes accordingly, the pitch rising slightly as the angle of wind flow across its face adjusts. New harmonics emerge while others fade, creating a live performance that no two listeners will ever hear exactly the same way. This is music in its purest form, unrehearsed, unrecorded, impossible to replay or preserve except in memory. The sand beneath your feet shifts and settles as you stand, adding its own quiet percussion to the ongoing symphony. Each grain that moves creates its own tiny acoustic event, usually too small to hear individually, but collectively contributing to the overall sonic texture of the landscape. You are not just a listener in this environment, but a participant, your every movement adding to the composition. Walking down the dune's leeward slope, you disturb larger cascades of sand, creating sudden bursts of higher frequency sound that pierce through the deeper fundamental tones. These avalanche events are like percussion crashes in the sand symphony, sudden and dramatic before fading back into the underlying hum. The sound follows you as you descend, Doppler shifting slightly as the vibrations travel through the moving sand dot at the base of the dune. You turn back to look up at the singing mountain. In the moonlight, it appears both solid and ephemeral, its edges softened by the gentle movement of wind grains. The song continues, will continue long after you have moved on. A patient performance for an audience of stars and silence. This encounter with the singing dunes has revealed another layer of the desert's hidden complexity. What appeared to be a simple landscape of sand and wind has revealed itself as an intricate acoustic ecosystem, where geology and physics combine to create art. The dunes are not silent witnesses to the passage of time, but active participants in an ongoing conversation between earth, air, and the fundamental forces that shape our world. As you walk away from the musical mountain, its song gradually fades, but doesn't disappear entirely. The lower frequencies travel farther, following you like a gentle hand on your shoulder, a reminder of the connection you've discovered between your own rhythms and those of the landscape. The sound merges with the whisper of wind through sand, the distant call of night birds, the soft percussion of your footsteps on the desert floor. Your journey continues into the deepening night, but now you carry with you the knowledge that the earth itself can sing, that beneath the apparent silence of wild places lies a rich acoustic world waiting to be discovered. The dunes have taught you to listen more carefully, to recognize the music that emerges when natural forces find their perfect expression in matter and motion. As the last notes of the dunes song fade into the ambient sounds of the desert night, you find yourself wondering about other hidden symphonies that might surround you, in the creak of cooling rocks, the whisper of wind through canyon walls, the subtle harmonics of water moving through underground spaces deep beneath your feet. Stand at the edge of vast emptiness, where silence has weight and the horizon dissolves into dreams. The desert stretches before you like an ancient manuscript, written in a language older than words, a language of curves and angles, of precise mathematics disguised as wilderness. Here, in this cathedral of sand and sky, you become witness to the universe's most patient artist. The wind. Feel the first gentle breath against your skin. This is not mere air moving from place to place, but a sculptor with invisible hands carrying tools of infinite precision. Each grain of sand becomes both chisel and stone, each gust a deliberate stroke across the canvas of earth. You close your eyes and listen to the whispered conversations between elements wind, speaking to sand in frequencies that make mountains bow and valleys sing. The wind begins its work with the smallest gestures. Individual grains lift and dance, following paths that seem random, but are governed by laws as absolute as gravity itself. Watch how they move in patterns that mirror the spirals of galaxies, the chambers of nautilus shells, the arrangement of leaves on a stem. This is not coincidence, but cosmic choreography, mathematical poetry written across the desert floor. You kneel and observe the sand, ripples forming beneath the wind's caress. These are not simple waves, but manifestations of the Fibonacci sequence nature's secret code revealing itself through granules of quartz and feldspar. Count the ridges as they emerge. 1, 1, 2, 3, 5, 8, 13. Each number the sum of the two before it, each pattern a whisper of the golden ratio that governs sunflower seeds and spiral galaxies alike. The wind grows stronger, more confident in its artistry. It gathers sand into streams that flow like liquid mercury across the desert surface. These rivers of particles follow the paths of least resistance, carving channels that branch and merge in patterns identical to river deltas, lightning bolts, and the neural networks in your dreaming brain. The mathematics of fluid dynamics plays out in miniature dramas, each grain a character in an epic of erosion and creation. As you watch, larger forms begin to emerge. Sand dunes rise like sleeping giants, their profiles following the mathematical curves that engineers call optimal, the catenary arch, the logarithmic spiral, the hyperbolic paraboloid. These shapes appear wherever forces seek balance, wherever energy finds its most efficient expression. The dune's windward slope climbs at precisely 34 degrees, the angle of repose where sand grains balance on the knife's edge between stability and avalanche. But it is the leeward face that holds the deepest mystery. Here, sand accumulates and slides in cascades that follow power laws, mathematical relationships that govern everything from earthquake magnitudes to the distribution of wealth. Small avalanches happen frequently, large ones rarely, but all follow the same underlying equation. The desert becomes a laboratory where chaos theory reveals its secrets through tumbling grains. You trace your finger along the dune's crest, feeling how the wind has carved an edge, so precise it could have been drawn with a ruler. This is this mathematical phenomenon called the angle of repose made visible, the exact degree at which loose material will naturally settle. 34 degrees, repeated in anthills and grain silos, in talus slopes and children's sandcastles. The wind knows this number instinctively, sculpting with the precision of a master geometer. The golden ratio emerges everywhere your eyes settle. Measure the height of a dune against its base often, you'll find 1.618, the divine proportion that ancient Greeks believed held the secret of perfect beauty. The spiral arms of sand devils trace logarithmic curves that match the shape of hurricanes. And the arms of galaxies. What appears as random wilderness reveals itself as a vast computation. The Earth itself solving equations through the patient movement of its elements. As afternoon light slants across the landscape, shadows become another medium for mathematical expression. They stretch and shift according to the laws of trigonometry, creating triangles and parallelograms that change with the sun's arc. The interplay of light and shadow transforms each dune into a sundial, marking time through geometry. You realize you are standing inside a vast natural calculator where every shadow computes the Earth's rotation. Every grain's position solves an equation of force and friction. The wind patterns themselves follow mathematical principles discovered by meteorologists and fluid dynamicists. Eddies and vortices form according to Reynolds numbers dimensionless, quantities that predict when smooth flow becomes turbulent. You cannot see these calculations, but you witness their results in the way sand swirls and settles, in the formation of temporary tornadoes that sketch helical paths across the desert floor. Temperature gradients create their own mathematical dramas. As the sand cools in evening air, convection currents rise and fall in patterns that mirror those in boiling water. In stellar atmospheres, in the mantles of planets, the heat flows according to Fourier's equations, invisible rivers of thermal energy that shape the visible world above. Each grain of sand becomes a tiny heat engine, expanding and contracting in rhythms that contribute to the desert's slow metamorphosis. You lie back against the warm sand and contemplate the fractal nature of what surrounds you. Zoom in on a single ripple, and you find smaller ripples. Zoom out to see the entire dune field, and the same patterns repeat at larger scales. This self-similarity spans orders of magnitude from microscopic crystal structures to continental geological formations. The mathematics of fractals reveals why natural forms feel so fundamentally beautiful to human perception. They echo the recursive patterns wired into our neural architecture. The chemistry of sand itself tells mathematical stories. Silicon dioxide. Crystals arrange themselves in tetrahedral lattice, three-dimensional puzzles solved by atomic forces. Each grain's surface bears the scars of countless collisions, its edges rounded according to probability distributions that describe how energy dissipates through matter. Under the microscope, sand becomes a library of mathematical trauma, each particle, a record of forces applied and absorbed over geological time. As darkness approaches, the wind's work becomes more subtle, but no less mathematical. Microclimates form around obstacles rocks. Plants, the footprints you've left behind. These create pressure differentials that follow Bernoulli's principle, causing sand to erode from some areas and accumulate in others. The desert breathes according to equations of fluid dynamics, inhaling and exhaling particles in cycles that span minutes and millennia alike. You feel the temperature dropping as the sun disappears, and witness another mathematical phenomenon, the exponential cooling described by Newton's law of thermal equilibrium. The sand releases its stored heat into the night sky, radiating energy according to the Stefan-Boltzmann law. Each grain becomes a tiny star, glowing invisibly in infrared frequencies as it surrenders the day's solar gift to the cosmic cold. The stars emerge overhead, and you realize the mathematics continues upward without pause. The same gravitational equations that shape sand dunes also govern planetary orbits. The same fluid dynamics that create wind patterns also drive the nuclear fusion in stellar cores. The desert becomes a gateway to understanding the mathematical unity that connects the smallest grain to the largest galaxy. In the growing darkness, you sense rather than see the continued work of wind and mathematics. Grains continue their ancient migrations, following paths prescribed by chaos theory, deterministic but unpredictable, ordered but never precisely repeatable. Each night's work erases some patterns while creating others, the desert existing in constant mathematical flux between order and randomness. The silence deepens, but you now understand it differently. This is not empty quiet, but the sound of countless calculations being performed, grains finding their angles of repose, thermal energy finding equilibrium, gravitational and electromagnetic forces finding balance. The desert hums with the frequency of pure mathematics, a symphony played in equations rather than notes. As you prepare to sleep under this canopy of stars, you carry with you a new understanding of beauty. The patterns that please your eye, the graceful curve of a dune's edge, the spiral of a sand devil, the geometric precision of ripples. These are not arbitrary aesthetics, but reflections of mathematical truth. Your brain recognizes beauty in these forms because it has evolved to detect the underlying order, to find meaning in the mathematics that governs all natural systems. The wind continues its patient work around you, sculpting dreams in sand and time. Each grain that moves tonight follows laws discovered by Newton and Einstein, by Fibonacci and Mandelbrot. The desert reveals itself as a vast analog computer, solving differential equations through the simple movement of particles, computing the future one grain at a time. You close your eyes and feel yourself becoming part of this grand calculation. Your breathing synchronized with the wind's rhythm, your heartbeat marking time against the desert's slower pulse. In the space between sleeping and waking, you sense the mathematical currents that flow through all things, from the spiral of your inner ear to the spiral arms of distant galaxies, from the branching patterns of your lungs to the branching patterns of lightning and rivers. The last conscious thought you hold is of connection, how the same mathematical principles that shape sand dunes also shape the neural networks through which this very thought travels. And you wonder what other hidden calculations govern the mysterious landscape of consciousness itself. Standing in the deep quiet of the desert night, you begin to perceive something extraordinary, a revelation that transforms your understanding of everything around you. What appears to be the ultimate expression of stillness, these towering dunes frozen against the starlit sky, is actually engaged in constant, purposeful movement. You are witnessing one of nature's most patient performances, a dance so slow that human lifespans can barely register its choreography. Close your eyes and imagine time itself stretching like warm honey, each second expanding into minutes, each minute flowering into hours. When you open them again, try to see the desert not as a snapshot frozen in time, but as a single frame from an impossibly long movie of film where mountains of sand flow like rivers, where entire landscapes migrate across continents with the persistence of glaciers, where the very ground beneath your feet participates in journeys that span millennia. The dune nearest to you, rising perhaps 60 feet into the night sky, appears as solid and permanent as any natural monument. Yet if you could compress centuries into seconds, you would see it flowing like slow water, its grains cycling from base to crest to lee side in an endless conveyor belt of motion. The dune is not a thing but a process, not a structure but a pattern that maintains its shape while constantly renewing its substance. This revelation begins with understanding how sand moves not randomly, but according to principles as precise as those governing the flow of rivers. Wind striking the windward face of a dune creates a zone of acceleration, picking up grains and carrying them up the gentle slope. These particles, each one a tiny sphere or crystal, follow ballistic trajectories as predictable as any projectile, landing on the dune's crest where they accumulate until gravity and the angle of repose, that critical slope where loose material can no longer maintain stability, triggers tiny avalanches down the steep lee face. You walk closer to observe this process in the gentle night breeze. Even now, in this relatively calm air, individual grains are making their microscopic journeys. You can hear the faint whisper of sand in motion, a sound like distant rainfall, as particles roll and bounce and saltate, that distinctive hopping motion that transports sand grain by grain across vast distances. Each tiny impact sends other grains into motion, creating cascading effects that ripple through the entire dune system. The physics governing this movement is elegantly simple, yet profound in its implications. Wind speed determines which grains can be lifted. Fine particles rise easily, while larger grains require stronger gusts. The shape and density of each grain affects its aerodynamic properties, influencing how far it will travel before settling. Surface roughness, moisture content, and even the electrostatic charges that build up between particles all play roles in this grand migration. But here's where the desert reveals its most astounding secret. These individual grain movements, multiplied across millions upon millions of particles and extended across centuries, create migration patterns of breathtaking scale. Entire dune fields flow across landscapes like slow rivers of sand, following prevailing wind patterns with the inevitability of water flowing downhill. Satellite imagery has revealed dune systems that travel hundreds of miles over decades, carrying millions of tons of sand from one region to another in a migration as purposeful as any animal journey. You begin to walk along the base of the dune, and with each step, you're following the path of countless grains that have made this same journey. Over the centuries, the sand beneath your feet may have started its travels in mountains that are now worn to stones, carried by ancient rivers to seas that dried up millions of years ago, then lifted by winds and transported across entire continents to arrive at this precise spot on this particular night. The mathematics of sand transport reveals patterns that echo throughout nature. The relationship between wind speed and grain movement follows power laws, small increases in wind Velocity result in exponential increases in sand transport. This means that occasional strong winds, though rare, accomplish far more erosion and deposition than the gentle, constant breezes that blow most of the time. It's a principle that applies equally to rivers carrying sediment and to the way changes accumulate in any complex system. As you continue your nocturnal walk, you begin to notice subtle variations in the sand around you. Some areas feel firmer underfoot, while others allow your feet to sink deeper. These differences reflect the ongoing sorting process that wind performs on sand grains. Stronger winds carry away finer particles, leaving behind coarser grains that pack more tightly. Weaker winds deposit fine material in sheltered areas, creating looser, softer surfaces. The desert is constantly sorting itself, organizing its grains by size and weight with the precision of a cosmic sifting machine. The shapes of the dunes themselves tell stories of wind direction and strength accumulated over years. Crescent-shaped, Martian dunes form where winds blow consistently from one direction, their horns pointing downwind like arrows indicating the sand's path. Linear dunes stretch for miles where winds blow from two directions, creating parallel ridges that channel airflow between them. Star dunes, with their multiple arms radiating from central peaks, develop where winds come from many directions, causing the sand to pile up in complex, three-dimensional sculptures. You pause to examine the surface of a nearby dune face, and even in the dim starlight, you can see the delicate ripples that pattern the sand like frozen waves. These ripples are miniature versions of the dunes themselves, formed by the same processes, but at a smaller scale. They migrate across the dune surface, just as the dunes migrate across the landscape. Tiny rivers of sand flowing over larger rivers of sand in a fractal display of motion at multiple scales. The time scales involved in these movements stretch your perception of what motion means. While water in a river might travel miles in a day, sand in a dune might travel the same distance over years or decades. Yet both follow similar principles of fluid dynamics. Both respond to gradients of energy and pressure, both carve channels and deposit sediments according to their capacity to carry material. Scientists have discovered that some of the world's largest dune systems are essentially rivers of sand that have been flowing for millions of years. The vast erg systems of the Sahara, covering areas larger than entire countries, represent sand streams that have maintained their general courses for geological ages, even as individual dunes within them constantly change shape and position. These are rivers without banks, flowing not downhill but downwind, carrying their sediment load not in solution, but in suspension and saltation. Standing here in the darkness, you begin to sense the patience required to perceive these movements. Human consciousness evolved to track the quick movements of predators and prey, the rapid changes of weather and season, struggles to comprehend processes that unfold over centuries. Yet once you adjust your temporal perspective, the apparent stillness of the desert reveals itself as a symphony of motion playing in ultra-slow tempo. You climb partway up the nearest dune, feeling how your feet sink into the loose sand of the lee face, evidence of the most recent avalanches that have carried grains from crest to base. Each step disturbs the angle of repose, triggering tiny flows of sand that whisper down the slope behind you. You are participating in the dune's migration, adding your small contribution to the eternal process of grain-by-grain movement that will, over time, transport this entire mountain of sand to a new location. From this elevated position, you can see other dunes stretching into the distance, and you begin to understand that you're looking at a vast conveyor system. Sand eroded from rocks in distant mountains is transported by rivers to the sea, then lifted by onshore winds and carried inland to form coastal dunes. These dunes may then migrate inland, their sand eventually reaching inland desert systems, where it continues its journey moved by different wind patterns toward new destinations, hundreds or thousands of miles away. The realization dawns that the sand grain you held between your fingers earlier tonight might be on a journey that will take it across continents before it finally comes to rest, perhaps as part of a sandstone formation that will preserve its travels in stone, or perhaps as sediment on the floor of a future ocean. Some grains cycle repeatedly through this system, spending millennia as part of dunes, then being incorporated into rocks, then weathering out to begin their travels anew. The concept of deep time begins to feel less abstract as you contemplate these journeys. The dune you're standing on might occupy this precise location for decades or centuries, but it is merely passing through, a temporary configuration of sand grains that will eventually disperse to continue their individual odysseys. Yet the dune itself, as a pattern and process, might persist much longer, maintaining its essential form even as its substance constantly changes. This paradox permanence of pattern, combined with impermanence of substance, reveals itself as one of nature's fundamental principles. Rivers maintain their courses, even as the water within them constantly flows. Waves preserve their shapes, even as the water particles move in circles. Living organisms maintain their forms, even as their atoms are replaced. The dune you stand upon is another expression of this deep truth, that in a universe of constant change, stability comes not from static structure, but from dynamic equilibrium. Out as you make your way back down the dune, you notice how your footprints are already being modified by the gentle wind. Tomorrow's stronger thermal winds will likely erase them entirely, but your passage has become part of the dune's history, your small disturbance joining the countless disturbances that continuously reshape these flowing mountains of sand. The temperature continues to drop, and you can feel thermal currents beginning to shift as different surfaces cool at different rates. These subtle air movements, barely perceptible to your skin, are the engines that will drive tomorrow's sand transport. As the sun rises and heats the desert floor, more dramatic winds will develop, and the great migration will continue with renewed energy. You begin to understand that the desert's apparent emptiness is actually fullness, full of movement too. Slow for human perception, full of journeys too long for human comprehension, full of stories written in a language of angles and slopes and grain-size distributions. Every surface you see bears the signature of wind direction and strength. Every slope records the history of sand supply and transport capacity. The stars wheel overhead, marking the passage of hours that represent tiny increments in the desert's temporal scale. While you experience this night as a discrete event with beginning and end, the desert experiences it as a moment in an ongoing process that connects this evening to others, stretching back through geological time. The sand remembers not just the rocks from which it came, but every wind that has ever moved it, every storm that has ever scattered it, every calm period that has allowed it to rest. As you prepare to continue your journey deeper into the desert's mysteries, you carry with you this new understanding of motion and time. The ground beneath your feet is not solid but flowing, not permanent but transient, not still but engaged in movements so patient and persistent that they reshape entire continents grain by grain. You walk now not just on sand, but on the surface of a slow river that has been flowing since long before humans walked the earth, and will continue flowing long after the last human footprint has been erased by the eternal wind. And in this recognition of the desert's fluid nature, you find yourself wondering about other kinds of flows that might be invisible to your senses, currents of energy and information that move through the landscape in ways even more subtle than the migration of sand, patterns of connection, and communication that link every grain to every other grain in networks of relationship that span both space and time. You stand in the heart of the desert at that magical hour before dawn, when the sand beneath your bare feet holds the cool memory of night and the air shimmers with possibilities hidden from the harsh light of day. This landscape, which appears to your eyes as the definition of dryness itself, is about to reveal its most closely guarded secrets about water secrets written in underground rivers, morning dewdrops, and the ingenious survival strategies of creatures who have learned to find abundance in apparent scarcity. The silence around you is profound, but it is not empty. It hums with the quiet industry of 1,000 hidden water cycles, each one a testament to life's remarkable ability to find and conserve the most precious resource on Earth. As the first pale light touches the horizon, you begin to perceive the desert not as a place of absence, but as a masterpiece of water wisdom, where every grain of sand participates in an ancient choreography of conservation and collection. Beneath your feet, far below the sun-warmed surface layers, vast aquifers stretch like underground seas through porous rock formations that have been accumulating water for tens of thousands of years. These hidden reservoirs hold water that fell as rain during ice ages, when this now arid landscape was green with vegetation and crossed by flowing rivers. The water seeps slowly through soil and stone, filtering down through layers of sediment, until it reached impermeable bedrock and collected in these subterranean chambers. This fossil water, as scientists call it, carries within its molecular structure the chemical signature of ancient climates. Isotope ratios tell stories of the temperatures and atmospheric conditions that existed when these water molecules first condensed from prehistoric clouds. Some of this water is older than the earliest human civilizations, older than the pyramids, older than written language itself, resting patiently in darkness while continents shifted and species evolved far above. The aquifers exist in different layers, some shallow enough that deep-rooted desert plants can tap into them with roots that extend down 30 feet or more, others buried so deep that they require modern drilling technology to access. Between these layers, the rock itself acts as both filter and storage system, purifying the water as it moves incredibly slowly through mineral matrices, sometimes traveling only inches per year on journeys that may take millennia to complete. As the sky lightens, you notice something remarkable beginning to happen to the sand around you. The individual grains, which radiated their accumulated heat into the clear night sky, have cooled to temperatures below the dew point of the surprisingly humid desert air. Water vapor, invisible and seemingly absent during the scorching day, begins to condense on these tiny crystalline surfaces, creating microscopic dewdrops that gleam like scattered diamonds in the early light. This process of dew formation represents one of the desert's most elegant water collection strategies. The sand grains act as countless tiny condensation surfaces, their high surface area to volume ratio maximizing the potential for water capture. Each grain becomes a miniature water harvester, pulling moisture from air that contains more humidity than most people realize. Even in the driest deserts, the air typically holds some water vapor, and the dramatic temperature swings between day and night create perfect conditions for this atmospheric water to condense. You kneel and examine the sand more closely, marveling at how each grain has become jeweled with captured moisture. The amount of water collected this way might seem insignificant to human perception, but for the desert's specialized inhabitants, this dew represents a reliable daily source of hydration. Beetles navigate across the sand dunes, positioning themselves to collect dewdrops on their specially textured wing covers. Lichens and cryptobiotic soil crusts absorb this moisture directly through their surfaces, beginning their daily photosynthesis powered by water. They literally pull from thin air. The phenomenon of atmospheric water harvesting extends beyond simple dew formation. Some desert plants have evolved leaves and stems with specialized surface textures that actively collect water from fog and humid air. These biological water collectors work on principles that engineers are now copying to create artificial fog, nets and atmospheric water generators, learning from millions of years of evolutionary innovation in water scarcity management. as the sun rises higher. You witness the daily drama of water conservation that plays out across the desert landscape. Plants that seemed dead and dormant suddenly show signs of activity as they absorb the night's collected moisture. Their cellular machinery springs into action, conducting photosynthesis and growth processes during these precious hours when water is available, then shutting down into survival mode as the moisture evaporates and the heat builds. The timing of these processes reveals the exquisite precision with which desert life has adapted to water scarcity. Many desert plants conduct their gas exchange and photosynthesis primarily during the cooler, more humid hours of dawn and dusk, keeping their pores closed during the heat of the day to prevent water loss. This temporal separation of water collection and water conservation represents one of evolution's most elegant solutions to the challenge of avalanche of surviving in arid environments. You begin walking across the desert floor, and with each step you discover new evidence of the sophisticated water management systems that operate here. The spacing between plants follows mathematical patterns that optimize water collection while minimizing competition. Desert shrubs position themselves at precise distances from one another, each one claiming a territory sized to capture enough seasonal rainfall to sustain its survival needs. The root systems beneath your feet extend far beyond what you can see, above ground, creating vast underground networks that can sense and respond to the smallest amounts of moisture. Some desert plants develop root systems with surface area hundreds of times larger than their above-ground biomass, creating extensive water collection infrastructures that can capture moisture from light rains before it evaporates or runs off. Root networks also form symbiotic relationships with soil fungi, creating even more extensive water and nutrient collection systems. The fungal threads, called mycorrhizae, extend the effective reach of plant roots and can transport water and minerals across surprisingly long distances underground. This creates a kind of underground internet of resource sharing that helps entire desert communities survive through drought periods. The soil itself tells stories of water conservation strategies refined over geological time. Desert soils often develop special crusts composed of cyanobacteria, lichens, and mosses that can absorb and retain moisture far more effectively than bare sand. These cryptobiotic crusts, living skins that cover the desert floor, spring to life within minutes of receiving moisture, conducting photosynthesis and nitrogen fixation that benefits the entire ecosystem. When rare rainstorms do arrive in the desert, you witness water management strategies that seem almost magical in their efficiency. Plants that appeared dead suddenly burst into bloom within hours, conducting entire life cycles in the brief window when water is abundant. Seeds that have waited years for the right conditions germinate simultaneously, creating temporary carpets of wildflowers that complete their reproduction and return to dormancy before the soil moisture disappears. The landscape itself has been shaped by water's power to create efficient collection and distribution systems. The arrangement of rocks and sediments creates natural water catchments that funnel precious rainfall toward areas where plants can best utilize it. Arroyos and washes that remain dry for months or years suddenly become rushing torrents during storms, distributing water and nutrients across vast areas before returning to apparent dormancy. Even the animals of the desert have evolved extraordinary water conservation abilities that seem to defy the basic requirements of mammalian physiology. Kangaroo rats can survive their entire lives without ever drinking liquid water, obtaining all their hydration from the metabolic processing of dry seeds. Their kidneys concentrate urine to levels that would be toxic to most mammals, and their respiratory systems recapture moisture from exhaled air with remarkable efficiency. Desert birds time their activities to take advantage of the temperature differentials that create opportunities for water collection. They position themselves where thermal currents create condensation, And some species have evolved behavioral patterns that allow them to predict and locate ephemeral water sources across vast territories. As the day progresses and you feel the increasing heat beginning to transform the landscape, you gain a deeper appreciation for the intricate timing that governs all desert water relationships. Every living thing here operates according to precise schedules that maximize water collection during brief favorable periods and minimize water loss during the harsh majority of time when conservation is paramount. The desert teaches that abundance and scarcity are often matters of timing and perspective rather than absolute quantities. What appears barren and lifeless reveals itself as extraordinarily rich and active when viewed with an understanding of the temporal rhythms that govern water availability. The seemingly empty landscape pulses with hidden cycles of collection, conservation, and careful expenditure that sustain complex communities of specialized organisms. Standing here as the heat begins to build toward its daily crescendo, you realize that the desert's water stories are ultimately stories about patience, precision, and the extraordinary creativity that emerges when life faces its greatest challenges. Every adaptation you've witnessed represents thousands of generations of innovation, each organism contributing to an ever-evolving symphony of survival strategies that transform limitation into opportunity. The water beneath your feet and in the air around you connects this moment to ancient ice ages and future rainstorms, to underground rivers and morning dewdrops, creating a web of temporal and spatial relationships that reveals the desert as not just a place of survival, but as a masterpiece of interconnected systems where every drop of water participates in stories larger than any individual organism can comprehend. You feel it first as a subtle tingling against your skin, a gentle lifting sensation that makes the fine hairs on your arms stand at attention like tiny antennae reaching toward something invisible yet present. The night air around you has begun to change, charged with an energy that transforms the desert from a simple landscape of sand and stone into something far more mysterious, a vast electrical field where every grain of sand becomes a miniature power source, every gust of wind a generator of invisible lightning. Walking through this charged landscape, you begin to understand that the desert is not merely a place where electricity occasionally visits during thunderstorms, but rather a continuous electrical ecosystem where charge builds, flows, and dances in patterns as complex and beautiful as any aurora. The very sand beneath your feet is alive with electrical potential, each grain a tiny battery waiting to discharge its stored energy into the night. The science behind this electrical awakening begins with the most fundamental of forces: friction. As you brush your hand along a rocky outcrop, you are participating in the same process that has been building electrical charge in this desert for millions of years. The contact between your skin and the stone creates a separation of electric charge, electrons flowing from one surface to another, leaving behind regions of positive and negative electrical potential that seek to reunite. But your touch is gentle, compared to the relentless electrical generation that occurs when wind moves sand. Each collision between grains creates a triboelectric event, a tiny spark of charge separation that occurs when different materials rub together. The word itself comes from the Greek tribine, meaning to rub, and electron, the ancient name for amber, which the Greeks discovered could attract small objects after being rubbed with fur. In the desert, this ancient phenomenon plays out on a massive scale. Every sand grain that tumbles across the surface, every particle that bounces in the wind, becomes part of an enormous electrical circuit. The grains are not uniform in their electrical properties. Some are naturally positive charge donors, others are negative charge acceptors. When they collide, electrons flow from one to the other, creating an electrical imbalance that accumulates grain by grain, collision by collision. You pause to examine a handful of sand, letting the grains flow between your fingers. In the moonlight, they appear innocent enough, But you now know that each tiny crystal is electrically active. Quartz grains, which make up much of desert sand, are particularly effective at generating static electricity. Their crystalline structure makes the natural piezoelectric materials they generate electrical charge when subjected to mechanical stress. Every time these grains are compressed, twisted, or struck by other particles, they release tiny amounts of electrical energy. The size of the grains determines their electrical behavior. Smaller particles tend to become negatively charged, while larger ones typically become positive. This size-dependent charging means that when wind sorts sand by size lifting, the smaller grains higher while leaving larger ones closer to the ground. It creates vertical layers of different electrical charge. The desert air becomes stratified with electricity, positive charges accumulating near the surface, negative charges building in the dust clouds above. As you continue walking, a gentle breeze begins to stir the sand around your feet. With each gust, billions of microscopic electrical events occur. The wind doesn't just move sand, it transforms it into a living electrical conductor. The moving grains collide thousands of times per second, each impact creating a tiny spark of charge. Transfer. The accumulation of these countless micro-lightning events builds into measurable electrical fields that can extend hundreds of meters into the air above the desert floor. The electrical field strength in a dust storm can reach extraordinary levels, sometimes exceeding 100,000 volts per meter, approaching the electrical intensity found in thunderclouds. Yet this power remains largely invisible to the human eye, expressing itself through subtle phenomena that require careful observation to detect. You might notice your hair beginning to stand on end, or feel a slight shock when you touch metal objects. But the full electrical drama playing out around you operates mostly beyond the range of human senses. Scientists have discovered that these electrical fields can be detected and measured using specialized instruments, revealing the desert as a vast electrical landscape with its own weather patterns, currents, and storms. The electrical activity follows daily rhythms, building during the heat of the day when thermal winds are strongest, then often reaching peak intensity during the evening hours when temperature differences create powerful air movements across the desert surface. You sit on a boulder and watch as a small dust devil begins to form in the distance. This spinning column of air and sand is not just a meteorological phenomenon, but an electrical one as well. As the dust devil draws sand and debris into its rotating column, the friction between particles creates an intense electrical charge. The spinning motion acts like a giant Van de Graaff generator, separating positive and negative charges and concentrating them in different parts of the vortex. The dust devil moves across the landscape like a walking lightning rod. It's electrical field so intense that it can interfere with radio communications and create electromagnetic signatures detectable from miles away. At its base, where sand grains are most concentrated and friction is highest, the electrical field strength can reach levels that would make your hair stand completely on. And if you were close enough to experience it directly. As the dust devil dissipates, it leaves behind a trail of electrically charged particles that slowly discharge their energy back into the environment. This discharge doesn't happen all at once, but occurs gradually through a process called corona discharge, a gentle bleeding of electrical energy that creates a subtle glow around charged objects. In the darkness of the desert night, this glow is usually too faint to see with the naked eye, but it represents the visible manifestation of the electrical forces at work all around you. The electrical properties of sand are influenced by more than just grain size and friction. Moisture content plays a crucial role in determining how effectively sand can build and maintain electrical charge. Dry sand is an excellent insulator, allowing electrical charge to accumulate and persist for long periods. But even tiny amounts of moisture can dramatically change the electrical behavior of sand. providing pathways for charge to flow and dissipate. This is why the most dramatic electrical phenomena in deserts often occur during the transition periods between wet and dry seasons, or during the daily cycles when humidity levels change. As the night air around you cools, it may carry just enough moisture to begin affecting the electrical properties of the sand, creating conditions where accumulated charge can suddenly find new pathways to flow. The electrical activity in desert environments creates its own unique electromagnetic signature. This signature can be detected by satellite instruments, allowing scientists to study electrical storms in deserts from space. The electromagnetic emissions from electrically active sandstorms can interfere with radio communications over vast distances, creating a form of natural jamming that demonstrates the power of these seemingly small electrical events when they occur on a massive scale. You notice that certain areas of the desert seem more electrically active than others. Rocky outcrops, where different types of stone meet, create natural electrical boundaries. Areas where sand has been recently disturbed by wind or animal activity show higher levels of electrical charge. Even the tracks you've left in the sand behind you have different electrical properties than the undisturbed surface around them. The electrical landscape of the desert is three-dimensional, extending not just across the surface, but deep into the sand and high into the air above. Underground, the electrical properties of sand layers create complex patterns of charge distribution. Some layers may be naturally more conductive than others, creating underground electrical pathways that can channel charge across vast distances. Above ground, the electrical field extends upward, sometimes reaching heights of several hundred meters, creating an invisible electrical dome over the desert landscape. Birds and other animals that live in desert environments have evolved to navigate and respond to these electrical fields. Many species can detect the electrical signatures of approaching dust storms long before they become visible, using this early warning system to seek shelter or adjust their behavior. Some insects use the electrical fields as navigation aids, following electrical gradients the way migrating animals follow magnetic fields. The electrical properties of sand also interact with other natural phenomena in unexpected ways. Solar radiation can affect the electrical conductivity of sand grains, creating daily cycles of electrical activity that correspond to patterns of sunlight and shadow. Cosmic radiation from space can ionize particles in the upper atmosphere above deserts, creating cascading effects that influence the electrical behavior of sandstorms below. As you walk through this electrically active landscape, you are participating in a vast natural experiment in physics and chemistry. Your body, being mostly water and salt, acts as a conductor in this electrical environment. You become part of the circuit, a mobile electrode that can detect and respond to the electrical fields around you. The tingling sensation you feel, the way your hair responds to the charged air, the slight shocks you might experience, all of these are evidence of your integration into the desert's electrical ecosystem. The lightning-like discharges that occur between sand grains are too small and brief to see individually, but they follow the same physical principles as the dramatic lightning bolts that illuminate thunderstorms. Each tiny spark represents a momentary equalization of electrical potential, a brief flow of electrons seeking balance. When millions of these micro-lightning events occur simultaneously during a dust storm, they create electromagnetic pulses that can be detected by sensitive instruments from great distances. The temperature of the sand affects its electrical properties in complex ways. Hot sand can hold more electrical charge than cold sand, but it also provides better pathways for that charge to flow and dissipate. The optimal conditions for electrical activity often occur during the evening hours, when the sand is still warm from the day's heat, but the air has begun to cool, creating temperature gradients that drive both wind formation and electrical charge separation. You pause to place your hand flat against the sand, feeling for the subtle vibrations that indicate electrical activity beneath the surface. The sand feels warm against your palm, and you imagine you can sense the microscopic lightning events occurring just beneath your touch. This is the electrical heartbeat of the desert, a rhythm of charge and discharge that has been pulsing through this landscape since the first grains of sand began their endless dance with the wind. The study of electrical phenomena in desert environments has practical applications beyond pure scientific curiosity. Understanding how electrical charge builds up in sand and dust can help engineers design better protection systems for electronic equipment in desert regions. It can also aid in predicting when and where electrical storms might interfere with communication systems or navigation equipment. As you continue your nighttime journey through this electrically charged landscape, you carry with you a new appreciation for the invisible forces that surround us. The desert has revealed itself not just as a place of sand and stone, but as a vast electrical instrument, continuously generating and conducting the fundamental forces that bind matter together and drive the physical processes of our world. Electrical fields that dance through the desert air around you are part of the same electromagnetic spectrum that carries radio waves, enables wireless communication, and connects all electronic devices. In experiencing the natural electrical phenomena of the desert, you are witnessing the raw, unfiltered version of the forces that power our technological civilization. The night air continues to tingle against your skin as you walk, each step creating tiny electrical disturbances in the sand beneath your feet. You have become part of the desert's electrical circuit, a conductor of the ancient forces that shape our world. As you move through this charged landscape, you find yourself wondering about the other electrical phenomena that might be occurring unseen around you. The electrical activity in your own nervous system, responding to the environment. The electromagnetic fields generated by your heartbeat, interacting with the electrical fields of the desert. The cosmic electrical forces that connect this small patch of electrified sand to the vast electrical systems of planets, stars, and galaxies beyond. The first whisper of dawn touches the eastern horizon, and you witness the desert's most intimate magic, the birth of color from colorless light. In these precious moments before the sun fully emerges, you discover that what you've always called sand color is actually an entire universe of hidden hues, waiting for the right angle of illumination to reveal their secrets. You kneel beside a seemingly ordinary patch of desert floor, your face close enough to see what casual observation would miss. Each grain of sand becomes a miniature cathedral of crystal, built from silicon and oxygen atoms, arranged in precise geometric lattice. These are not simple brown pellets, but complex optical instruments, each one a tiny lens and prism combined, capable of bending light in ways that would make a physicist weep with wonder. The pre-dawn light arrives at a shallow angle, and suddenly the sand begins its chromatic symphony. What appeared uniform beige in yesterday's harsh noon sun now reveals itself as a tapestry of rose quartz pink, smoky topaz amber, clear crystal white, and deep garnet red. You realize you are witnessing the desert's secret, how light and matter conspire to create the illusion of color in a universe where color, technically, does not exist. Pick up a single grain and hold it to the growing light. This transparent crystal, no larger than a period on a page, contains the entire electromagnetic spectrum within its boundaries. When white light from the sun strikes its surface, the grain becomes a prism, separating that white light into its component wavelengths according to Snell's law of refraction. Blue light bends more sharply than red, creating microscopic rainbows that dance across surfaces too small for your naked eye to resolve. But the magic deepens beyond simple refraction. Each grain's surface bears microscopic imperfections, tiny fractures, inclusions of other minerals, coatings of iron oxide that formed over millennia of chemical weathering. These imperfections become filters, absorbing certain wavelengths while allowing others to pass through or reflect back toward your eye. The result is a grain that might appear golden from one angle, silver from another, and deep burgundy when the light strikes it just so. You move your head slightly and watch how the entire landscape shifts in response. This is not your imagination, but the physics of Fresnel reflection at work, the same phenomenon that makes wet pavement more reflective than dry. That creates the polarized light that navigates migrating birds. The angle between the incoming light, the grain's surface, and your eye determines which wavelengths reach your retina, which colors your brain will construct from the electromagnetic information dot. As the sun climbs higher, you observe how different minerals within the sand contribute their own chromatic signatures. Feldspar crystals flash with blue and green iridescence, their internal structure creating interference patterns that cancel some wavelengths while amplifying others. Mica flakes catch the light like tiny mirrors, their perfectly cleaved surfaces, reflecting pure white light in brilliant flashes that momentarily blind and dazzle. The iron oxides tell their own colorful story. Hematite stains some grains deep red, the same mineral that colors Mars and ancient cave paintings. Magnetite creates blacks so deep they seem to absorb light itself, while limonite contributes yellows and browns that shift toward orange as the sun's angle changes. Each oxide represents a different chapter in the grain's chemical history, a record of the atmospheric conditions under which it formed and weathered. You notice how humidity affects the display of colors. The slight moisture in the pre-dawn air creates thin films of water around each grain, and these microscopic layers become additional optical elements. They create interference patterns similar to those in soap bubbles, where the thickness of the water film determines which colors are enhanced and which are diminished. As the air dries with the rising sun, these ephemeral colors fade, leaving behind the more stable hues created by the mineral composition itself. The growing light reveals another optical phenomenon, how particle size affects color perception. The finest grains scatter light differently than larger ones, following Rayleigh's scattering principles. This is why distant mountains appear blue, and why sunset colors seem to pool in the spaces between larger sand formations. The smaller particles preferentially scatter shorter wavelengths, creating subtle blue and violet hazes that hover just above the desert surface like visible ghosts of electromagnetic radiation. As you watch, wind-blown dust creates temporary veils that filter the sunlight, acting like colored gels in nature's photography studio. These suspended particles remove certain wavelengths from the light before it reaches the sand, fundamentally altering the palette available for reflection and refraction. The entire desert becomes a dynamic optical instrument, its colors shifting, not just with the sun's angle, but with atmospheric conditions that change. Moment by moment, you begin to understand that the color of sand is not a property of the sand itself, but a collaborative creation between matter, light, and consciousness. The grains provide the physical structure, the atomic arrangements that interact with electromagnetic radiation in predictable ways. The light provides the energy photons carrying specific wavelengths that correspond to what humans perceive as color. But color itself emerges only in the interaction between these photons and the visual processing centers of your brain. Each wavelength of light carries its own energy signature. Violet photons pack nearly twice the energy of red ones, a difference that becomes crucial in understanding why some colors fade faster than others under the desert sun. The high-energy blues and violets can break chemical bonds, gradually bleaching organic pigments and altering the crystal structure of some minerals. The landscape you see today is partly the result of photochemical reactions that have been occurring grain by grain, photon by photon, for millions of years. The crystalline structure of quartz itself contributes to the optical complexity. Silicon dioxide can form in different ways. Some grains are single crystals with uniform optical properties, while others are polycrystalline aggregates that scatter light in multiple directions. Some contain microscopic inclusions of other minerals, creating internal optical interfaces that split and reflect light in patterns unique to each grain. Under a microscope, sand becomes a collection of tiny kaleidoscopes, each one creating its own private light show. You observe how the angle of the morning sun creates different color zones across the undulating sand surface. The windward faces of ripples catch direct light, revealing the bright whites and golds of forward scattered illumination. The leeward sides fall into shadow, but rather than appearing simply dark, they glow with the soft blues and purples of skylight sunlight that has been scattered by atmospheric particles and reflected down from the dome of the sky itself. Temperature plays its own role in this chromatic theater. As the sun warms the sand, thermal expansion slightly alters the spacing between atoms in the crystal lattice. This changes the way light interacts with the material, subtly shifting the wavelengths that are absorbed and reflected. The color changes are too subtle for conscious perception, but they occur nonetheless, the desert literally changing its colors with the temperature, like a vast mood ring responding to the sun's caress. The surface texture of each grain affects its optical properties through principles of geometric optics. Perfectly smooth surfaces create specular reflection, mirror-like bouncing of light that preserves the original color and intensity. But most sand grains have surfaces roughened by countless collisions, creating diffuse reflection that scatters light in all directions. This diffuse scattering is what makes sand appear matte rather than shiny, and it's also what allows you to see colors from multiple viewing angles rather than just bright flashes of reflected sunlight. As you study individual grains more closely, you begin to notice their transparency variations. Some are nearly clear, allowing light to pass through and illuminate internal structures. Others are translucent, creating soft glows like natural lampshades. Still others are opaque, reflecting light only from their surfaces. These transparency differences create depth in the visual texture of sand, with light penetrating to different levels and creating subtle shadows and highlights within the granular matrix. The phenomenon of birefringence appears in some of the more exotic grains minerals that split light into two rays traveling at different speeds through the crystal. This creates a doubling effect, where a single grain might appear to contain two slightly offset images when viewed through polarized light. While invisible to normal observation, this property contributes to the complex ways that sand surfaces interact with the polarized components. Years. Thin layers might represent brief episodes of different conditions, periods of rapid climate change when environmental conditions shifted quickly from one state to another. Some of the most interesting climate information is preserved in the microscopic details of these rock layers. Tiny crystals within the rock can reveal the temperature and pressure conditions under which they formed. The isotopic composition of minerals can indicate the source of the water from which they crystallized, revealing whether ancient seas were more or less salty than today's oceans, or whether precipitation patterns were different in past climates. Pollen grains preserved in certain rock layers provide incredibly detailed information about ancient vegetation and climate. These microscopic fossils can reveal seasonal temperature patterns, rainfall amounts, and even the atmospheric carbon dioxide levels that existed when the pollen was originally deposited. Each grain of fossil pollen is like a tiny time capsule, preserving information about the specific plant that produced it and then the environmental conditions under which it lived. The spacing and arrangement of fossils within rock layers can reveal information about ancient seasonal cycles and long-term climate patterns. Mass mortality events preserved in the rock record might indicate sudden climate changes, volcanic eruptions, or other environmental catastrophes that affected entire ecosystems. The distribution of different species through various rock layers shows how plant and animal communities responded to gradual climate changes over geological time. Above the older rock layers, newer deposits tell stories of more recent climate changes. Layers of ancient sand dunes, now cemented into stone, reveal periods when this landscape was already becoming more arid. The cross-bedding patterns in these fossilized dunes show the direction of ancient winds, preserving a record of atmospheric circulation patterns from millions of years ago. Some layers contain evidence of ice ages periods when global climate was much cooler than today. During these cold epochs, different patterns of erosion and deposition created distinctive rock layers with unique mineral compositions and sedimentary structures. The absence of certain types of fossils in these layers indicates how plant and animal communities adapted to or disappeared during periods of global cooling. The most recent layers in this geological archive tell of the climate changes that led to today's desert conditions. The transition from older, more varied rock types to the younger, more uniform deposits reflects the gradual drying of this landscape as continental positions shifted, mountain ranges rose, and global climate patterns evolved into their current configuration. Standing before this natural library, you realize that the desert around you is not an ancient, unchanging landscape, but rather the most recent chapter in a continuously evolving story. The dunes that surround you are temporary features that will themselves eventually be compressed into rock layers, adding new chapters to this vast geological archive for future readers to discover and interpret. The wind and sand that have revealed. These layers continue their work of writing new pages in Earth's climate history. Every grain of sand that moves across the desert surface carries with it chemical signatures of current atmospheric conditions, isotopic traces of today's precipitation patterns, and microscopic fossils of contemporary plant and animal life. These materials will eventually be deposited in new layers that will preserve a record of our current climate for future generations to study. The rock layers before you represent not just past climates, but also the fundamental processes that continue to shape Earth's climate system today. The same forces that created these ancient deposits, solar radiation, atmospheric circulation, ocean currents, volcanic activity, and the slow drift of continents continue to influence our planet's climate, though on timescales that dwarf human experience. As you step back from this natural archive, you carry with you a new understanding of the desert as a repository of Earth's deep memory. The landscape around you is not just sand and stone, but a vast library containing the recorded history of our planet's climate, written in a language of minerals and fossils that scientists are still learning to read with ever greater precision. And understanding. The silence of the desert night seems different now, filled with the whispered stories of ancient seas and forests, of ice ages and tropical epochs, of the countless climate changes that have shaped this landscape over millions of years. You walk forward into the continuing story, knowing that the sands beneath your feet will someday become the next chapter in this endless geological narrative, preserving for future readers the climate story of our own time. You stand beneath a canopy of stars that seem closer than ever before, your feet still planted in terrestrial sand, but your consciousness expanding outward into the vast choreography of worlds that dance through space around your sun. The grains beneath your toes whisper not just of Earth's geological stories now, but of a much grander narrative one, written in the dunes of distant planets and the seasonal rhythms that pulse through every corner of your solar system, like a cosmic heartbeat connecting you to realms you've never seen but somehow recognize. The wind that moves the sand around your ankles carries with it an invitation to understand that the patterns you've been discovering, the migration of dunes, the sorting of particles, the eternal dance between gravity and atmosphere, are not unique to this blue world, but represent fundamental principles that operate wherever matter encounters motion across the universe. Tonight, your journey transcends the boundaries of Earth's atmosphere to explore sand seas that stretch across alien landscapes under foreign skies. Mars calls to you first, that rust-colored wanderer whose seasons stretch nearly twice as long as Earth's, where massive dust storms can engulf the entire planet for months at a time. You close your eyes and let your imagination carry you across the void to stand on the Martian surface, where beneath your feet spreads a different kind of sand iron oxide particles that give the planet its characteristic red hue, each grain a microscopic piece of ancient oxidation that tells the story of a world that lost its protective magnetic field billions of years ago. The Martian sand beneath your imagined feet feels different from Earth's silicate grains. These iron-rich particles are angular and jagged, shaped by processes unfamiliar to your home world. Without liquid water to smooth their edges through countless cycles of erosion, without the chemical weathering that rounds Earth's grains into gentle curves, Martian sand retains the sharp memory of impact fracturing and thermal shock, of volcanic eruptions and meteorite bombardments that shattered rock into countless razor-edged fragments. Here on Mars, the seasonal rhythms operate on a scale that dwarfs Earth's annual cycles. As the planet follows its elliptical orbit around the Sun, taking nearly 2 Earth years to complete 1 Martian year, vast atmospheric changes reshape the landscape with patient persistence. The polar ice caps, composed of both water and frozen carbon dioxide, advance and retreat with the seasons, sublimating directly from solid to gas and back again, driving powerful atmospheric currents that lift billions of tons of sand into planet-wide dust devils and storms. You watch in your mind's eye as these Martian dust storms develop, beginning as small whirlwinds that grow and merge and feed upon themselves until they become continental in scope. The thin Martian atmosphere, less than 1% as dense as Earth's, nonetheless moves these iron oxide particles with remarkable efficiency. The lower gravity allows dust to remain suspended for months, creating towering columns of airborne sand that stretch into the tenuous upper atmosphere and circle the globe on jet streams that move at hundreds of miles per hour. The dunes of Mars migrate across the landscape, following patterns that echo those you've observed on Earth, yet operate according to the unique physics of reduced gravity and minimal atmospheric pressure. Martian dunes creep across the Martian plains, their crescent shapes responding to seasonal wind patterns that shift as the planet's axial tilt carries different hemispheres toward and away from the distant sun. These alien sand formations move more slowly than their terrestrial counterparts, but with the same fundamental mathematics governing their shapes and their patient journeys across the landscape. From Mars, your consciousness expands further outward, beyond the asteroid belt, to the realm of the gas giants, where Saturn's largest moon, Titan, beckons with its own unique sand story. Here, in the frigid outer reaches of the solar system, methane plays the role that water plays on Earth, existing in all 3 phases, solid, liquid, and gas, creating weather patterns and erosion cycles that mirror your homeworld's processes, but operate with an alien chemistry. Titan's sand tells a story written in hydrocarbons rather than silicates. The particles that accumulate in vast dune fields near Titan's equator are composed not of weathered rock, but of organic compounds, complex carbon molecules that precipitate from the thick, nitrogen-rich atmosphere like snow, then are sculpted by methane winds into familiar dune patterns that span hundreds of miles. These hydrocarbon grains are darker than coal, absorbing the faint sunlight that filters through Titan's dense, orange atmosphere after traveling nearly 10 times farther from the sun than the light that warms Earth. The seasonal rhythms on Titan operate on a timescale that encompasses nearly 30 Earth years for each complete orbit around the sun. As Titan follows Saturn through its vast elliptical path, the moon experiences seasons of extraordinary duration, with winter and summer each lasting more than 7 Earth years. These extended seasons drive atmospheric circulation patterns that transport hydrocarbon particles from Titan's polar regions toward its equatorial dune fields, creating a slow but persistent sand migration that has been operating for millions of years. Standing in your imagination on Titan's surface, you feel the weak grip of gravity that is only 1/7 as strong as Earth's, allowing particles to remain airborne far longer than would be possible in your homeworld's denser atmosphere. The thick nitrogen atmosphere, 4 times denser than Earth's, creates winds that can move sand particles despite the reduced gravitational pull, generating dust devils and seasonal storms that reshape the hydrocarbon dunes with the same fluid mathematics that govern sand movement everywhere. Your mental journey carries you next to Venus, where the extreme greenhouse atmosphere has created conditions so hostile that traditional sand movement operates according to different rules entirely. The surface temperature of nearly 900 degrees Fahrenheit, hot enough to melt lead, and atmospheric pressure 90 times greater than Earth's, creates an environment where particles move through mechanisms unknown on any other world in your solar system. Venus's sand, composed primarily of basaltic minerals from extensive volcanic activity, experiences a kind of slow-motion fluid dynamics under the crushing atmospheric pressure. Particles move not just through wind action, but through processes that blur the boundary between solid and liquid behavior. The extreme conditions create unique erosion patterns and particle sorting mechanisms that operate on geological timescales, slowly reshaping the Venusian landscape through processes that challenge our understanding of how granular materials behave under extreme conditions. Even the gas giants themselves participate in the universal language of particle dynamics, though their sand consists of droplets and ice crystals suspended in their dense atmospheres. Jupiter's great red spot, a storm larger than Earth that has raged for centuries, demonstrates the same fluid dynamics and vortex mathematics that govern terrestrial dust devils and hurricanes, but operating on a scale and with a persistence that dwarfs any atmospheric phenomena on your home world. The seasonal patterns on Jupiter, driven by the planet's 11-year orbit around the Sun, create atmospheric circulation changes that affect the behavior of suspended particles throughout the giant planet's layered atmosphere. These patterns repeat with clockwork precision, each cycle bringing subtle shifts in the great storm systems that mix and sort the planet's atmospheric components, like a vast 3-dimensional sand dune that never quite settles into solid form. As your cosmic journey expands to encompass the outer reaches of the solar system, you discover that even the dwarf planets and asteroids participate in the universal grammar of particle movement and seasonal change. Pluto's thin atmosphere, composed primarily of nitrogen sublimating from surface ices, creates weak but measurable winds that slowly transport particles across the dwarf planet's surface according to its 248-year orbital cycle seasons that last longer than human lifetimes, creating changes so gradual that they can only be measured across multiple generations. The asteroid belt itself represents a kind of granular system operating on the largest possible scale, where individual asteroids behave like sand grains in a vast gravitational wind field created by the competing influences of the Sun and Jupiter. These rocky particles, ranging from pebble-sized meteoroids to mountain-sized asteroids, migrate and collide and fragment according to gravitational dynamics that mirror, on an enormous scale, the physics that govern sand movement in terrestrial dunes. Your awareness expands to encompass the realization that the solar system itself operates like a vast granular system, with planets and moons and asteroids, all responding to the gravitational fields and electromagnetic forces they create currents and eddies in the fabric of spacetime. The same mathematical principles that describe how sand grains move across a beach also govern how celestial bodies migrate through their orbits, how planetary rings sort themselves into gaps and divisions, how the solar wind carries charged particles across interplanetary space. The seasonal rhythms that you've been discovering on individual worlds reveal themselves as part of an even grander pattern, the slow circulation of the entire solar system. Around the galactic center, a journey that takes roughly 225 million years and creates what could be called cosmic seasons as your solar system moves through different regions of the Milky Way galaxy. These galactic seasons influence the flux of cosmic rays and interstellar particles that reach your solar system, creating cycles of change that operate on timescales so vast that they encompass the entire history of complex life on Earth. Once again on terrestrial sand, you feel the weight of this cosmic perspective settling around you like a comfortable blanket. The grains beneath your feet are no longer simply pieces of Earth's geology, but participants in universal processes that connect your moment of awareness to the grand rhythms that pulse through space and time. Every wind that moves sand across a dune participates in atmospheric circulation patterns that echo the storm systems of Jupiter. Every seasonal change that affects dune migration reflects orbital mechanics that govern the dance of worlds throughout the solar system. The iron in your blood was forged in stellar furnaces and distributed through interstellar space as cosmic dust before eventually condensing into the rocky materials that formed your planet. The silicon in the sand beneath your feet followed a similar journey, connecting this quiet moment of contemplation to the birth and death of stars, to the formation of solar systems, to the slow accumulation of heavy elements that made possible the existence of rocky planets and the complex chemistry of life. You realize that your journey through Earth's sand has been, from the beginning, a journey through universal principles that operate at every scale, from the quantum interactions that hold individual grains together to the galactic dynamics that shape the evolution of solar systems. The patterns you've learned to recognize, the mathematics of dune migration, the physics of particle sorting, the chemistry of weathering and erosion, represent fundamental aspects of how matter organizes itself in the presence of energy. Whether that energy comes from wind and water on Earth, or from stellar radiation and gravitational fields in the depths of space. As you prepare to transition from this cosmic perspective back toward the intimate scale of individual experience, you carry with you the understanding that every grain of sand participates in stories that span from the quantum realm to the cosmic scale, connecting your brief moment of awareness to the eternal rhythms that govern the behavior of matter and energy throughout the universe. The world holds its breath in the hour before dawn, and you find yourself suspended in a silence so profound it seems to have weight, texture, presence. This is not the mere absence of sound that city dwellers know, the brief gap between traffic noises or the muffled quiet of closed rooms. This is primordial silence, the kind that existed before the first word was spoken, before the first song was sung, before sound itself learned to travel through air. You sit motionless on the cool sand and gradually become aware that what you initially perceived as emptiness is actually fullness, a pregnant quiet that contains within it all the sounds that could be made but choose not to exist. The silence surrounds you like an invisible ocean, pressing gently against your eardrums, reminding you that your hearing has been shaped by millions of years of evolution to detect the smallest disturbances in the air's stillness. Listen deeper, and you begin to understand that silence is not the absence of vibration, but the presence of perfect balance. The air molecules around you are in constant motion, colliding and bouncing in random patterns that create no net pressure waves, no organized disturbances that your brain would interpret as sound. It is molecular democracy in its purest form, every particle moving freely, but collectively creating stillness. Your breathing becomes part of this meditation on emptiness and fullness. Each inhalation draws the desert's silence into your lungs, and each exhalation releases it back into the vastness. You notice how the rhythm of your breath creates tiny pressure variations in the air around you. momentary departures from perfect silence that dissipate like ripples in an infinite pond. Even your heartbeat adds its whispered percussion to the yao. Quiet, a biological drum keeping time in the cathedral of sand and sky. The silence begins to reveal its layers. Beneath what seems like absolute quiet, you detect the almost inaudible whisper of your own circulation blood flowing through vessels. So small they barely exist, yet carrying the chemical conversations that keep consciousness alive. Your nervous system hums with electrical activity below the threshold of hearing. Neurons firing in patterns that create thoughts, memories. The very awareness of silence itself, you realize that the space between sand grains mirrors the space between your thoughts. Just as each grain is separated from its neighbors by microscopic distances filled with air, each of your thoughts is separated from the next by gaps of pure awareness. Silent intervals where consciousness rests between the movements of mind. The desert has become a teacher of meditation, showing you how emptiness and substance interpenetrate at every scale. The silence deepens as the last vestiges of night fade toward dawn. In this threshold time, you understand that the desert's quiet is not empty but expectant. Like the pause between a conductor's raised baton and the orchestra's first note. The landscape around you exists in a state of potential sound wind that could rise to create music from sand and stone. Wildlife that could announce the coming day. Your own voice that could break the spell with a single word. But you choose silence, and in that choice, discover something profound about the nature of peace. The quiet does not impose itself upon you, but invites you into its embrace. You can resist it, fill it with internal chatter and mental noise, or you can surrender to it and let it fill the spaces between your thoughts with its own peculiar presence. Silence, you realize, requires no effort to maintain. It is the natural state to which all systems return when agitation ceases. Your awareness expands to encompass the vast acoustic space around you. Sound travels approximately 343 meters per second through air at this temperature, which means that if you were to shout into this silence, your voice would race across the desert at the speed of thought, creating spherical waves of pressure that would eventually dissipate into the infinite sky. But the silence absorbs even this hypothetical disturbance, demonstrating its capacity to contain all possible sounds without being diminished by them. The molecular physics of silence fascinates your quietly observing mind. Air at sea level contains roughly 25 quintillion molecules per cubic centimeter, all in constant thermal motion. In perfect silence, these molecules bounce off each other in completely random directions, creating a kind of acoustic white noise at frequencies too high for any ear to detect. The silence you experience is actually a narrow band of organized quiet, carved out of this molecular chaos, a human-scaled island of peace in an ocean of microscopic turbulence. You begin to notice how your own presence affects the silence. Your body radiates heat, creating subtle air currents that could, theoretically, produce the faintest whisper of convection. Your clothing shifts almost imperceptibly with each breath, fibers sliding against fibers in movements too small to hear, but large enough to exist. Even the moisture from your breath changes the local humidity, altering the speed at which sound would travel. If there were any sound to travel. The silence becomes a mirror, reflecting back the quality of your own inner stillness. When your mind races with thoughts and plans and memories, the external quiet seems somehow less profound, as if the tumult in your consciousness disturbs the peace around you. But when your thoughts settle into the same rhythm as your breathing, the silence deepens and reveals new dimensions of quietude that you hadn't noticed before. Time behaves differently in this depth of silence. Without the usual auditory landmarks, clocks ticking, traffic passing, voices speaking, your sense of duration becomes fluid, subjective. Minutes might pass like hours, or hours like minutes. The silence creates a pocket outside of measured time, where the present moment expands to fill all available space, where the concepts of before and after lose their urgency. You discover that silence has its own ecology. Just as forests have different types of quiet, the heavy hush of snow, the expectant stillness before storms, the peaceful rest of summer afternoons, the desert offers its own varieties of silence. This pre-dawn quiet differs qualitatively from the silence of noon heat, when the air shimmers with thermal currents, or the silence of night, when darkness adds its own acoustic weight to the stillness. The physical geography of silence becomes apparent as you notice how the gentle undulations of sand dunes create acoustic shadows areas where even the faintest sounds would be absorbed or deflected. The curved surfaces act like primitive sound baffles, designed by wind and gravity to enhance the natural quiet. You realize you are sitting in an amphitheater built for silence rather than sound, where the architecture itself serves the worship of Quiet. Your breathing synchronizes with some deeper rhythm, perhaps the expansion and contraction of the atmosphere as it warms and cools, perhaps the tidal pull of gravitational forces too subtle to name. In this synchronization, you find a kind of communion with the larger systems of which you are a part. Your personal silence becomes a note in the vast symphony of cosmic quiet that surrounds all things. The approaching dawn brings the faintest suggestion of change to the silence. Not sound exactly, but the potential for sound, the sense that the world is beginning to stir from its profound rest. Birds that do not yet sing shift on perches still hidden in darkness. Wind that does not yet blow gathers itself in atmospheric pressure differentials. The silence becomes pregnant with the day that is about to be born. You understand now that the desert's gift is not the temporary absence of noise, but the presence of something much more rare and precious, the opportunity to experience your own consciousness without the constant overlay of auditory stimulation. In the silence, you can hear the subtle processes of your own awareness, the way attention shifts from object to object, the way thoughts arise and dissolve, the way emotions create their own internal weather systems. The space between your thoughts expands, and in that expansion, you discover regions of awareness that are usually drowned out by the constant chatter of daily life. There are vast territories of inner experience that can only be explored in silent, subtle states of consciousness that require perfect quiet to emerge, like shy creatures that appear only when the human world has settled into stillness. As the first hint of light touches the eastern horizon, you realize that you have been sitting here not for minutes, but for what feels like eternities, suspended in the desert's masterclass on the nature of silence. The quiet has taught you that emptiness is not vacant, but full, that absence is a form of presence, that in the spaces between sounds lies the possibility of hearing what has always been there. Waiting, the silence begins to prepare for its eventual dissolution into the sounds of day, the wind's return, the distant call of a hawk, the whisper of sand moving across sand. But rather than ending, the silence simply transforms, becoming the foundation upon which all sounds will build, the vast acoustic space that will give context and meaning to whatever breaks its perfect surface. You carry this silence with you. Now, a portable sanctuary that exists not in any external place, but in the spaces between your own thoughts, in the pause between heartbeats, in the eternal moment that exists before each new breath begins its journey toward the light of sunlight. You notice how water, when present, transforms the entire optical equation. A grain of sand underwater appears dramatically different from the same grain when dry, not just because water has its own refractive properties, but because it eliminates the air-grain interfaces that create much of the scattering in dry sand. Wet sand appears darker and more saturated in color because light can penetrate deeper into the granular structure before being reflected back to your eye. The The desert's color palette expands as the sun rises higher and the light grows stronger. Colors that were muted in the dim dawn light now blaze with intensity as more photons per second strike each grain. But you also notice that harsh noon light, paradoxically, seems to wash out some colors, creating the bleached appearance that photographers call the dead light of midday. This happens because intense illumination overwhelms the subtle optical effects that create color variation. Just as bright headlights make it harder to see traffic lights at night, that atmospheric conditions add their own layers to the color story. Humidity affects not just the immediate surface of grains, but also the way light travels through the air itself. Dust particles suspended in the atmosphere act as additional optical elements, filtering and scattering light before it ever reaches the sand. On especially clear days, when the air is washed clean by recent weather, colors appear more saturated and pure. On hazy days, a soft filter seems to lie over the entire landscape, muting contrasts and creating the dreamy quality that desert photographers prize. You begin to perceive the desert as a vast, slow-motion fireworks display, where each grain is a tiny explosion of color happening at the speed of light. Photons arrive from the sun, having traveled 93 million miles in perfect electromagnetic formation, only to be scattered, absorbed, and reflected by crystalline structures smaller than the period at the end of this sentence. The colors you see are the debris from these microscopic collisions between light and matter, the electromagnetic exhaust of a trillion tiny optical engines dot as the morning progresses toward the harsh clarity of full daylight. You carry with you a new understanding of color as process rather than property. The golden sand, the red rock, the white salt flats, these are not fixed characteristics, but ongoing conversations between light and matter, temporary agreements between electromagnetic, radiation, and atomic structure. Every sunset changes the desert's color palette. Every passing cloud creates new combinations. Every grain of blowing sand adds or subtracts from the visual symphony. The colors that light forgot, you realize, are the ones that exist in potential in the wavelengths that our eyes cannot see, in the infrared heat signatures and ultraviolet patterns that paint the desert in spectra beyond human perception. But even within the narrow band of visible light, the desert reveals infinite complexity, a masterpiece painted with physics and chemistry, where every viewing angle opens new galleries of color and every moment brings fresh combinations of light and shadow, transparency and opacity, reflection and refraction. You close your eyes and let the growing warmth of the sun wash over your face, knowing that when you open them again, the colors will have shifted once more. The eternal dance between electromagnetic radiation and crystalline matter, creating new beauty with each passing moment of this desert dawn. You kneel beside an exposed cliff face where wind and time have carved away the surface layers, revealing the desert's secret library, a vertical archive of ancient worlds written in bands of stone and sediment. Each stripe of color, each change in texture represents a chapter in Earth's autobiography that spans millions of years. Here, pressed between layers of rock, are the preserved memories of climates so different from today's desert that they seem like stories from another planet entirely. Running your fingers along the smooth face of sandstone, you trace lines that were once the shoreline of a vast inland sea. The rock beneath your touch was formed when this entire landscape lay submerged beneath warm, shallow waters teeming with life. The fine grains that now make up this solid stone were once sand and silt settling slowly through ancient ocean depths, carrying with them the chemical signatures of long-vanished atmospheres and the fossil remains of creatures that swam in seas that no longer exist. The lowest visible layer speaks of a time when the Earth's climate was dramatically warmer than today. This red sandstone formed during a period when there were no polar ice caps, when palm trees grew in Antarctica, and when the ancestors of today's deserts or lush, humid landscapes crossed by meandering rivers. The iron oxides that give the rock its rusty color tell of oxygen-rich atmospheres and wet climates where metals could oxidize freely. In the presence of abundant moisture, above this ancient foundation lies a band of limestone, its pale gray surface smooth as marble, where centuries of wind have polished it. This layer carries within its crystalline structure the compressed remains of countless marine organisms, corals, shells, and microscopic sea creatures, whose calcium carbonate skeletons accumulated on ocean floors over millions of years. The limestone speaks of warm seas and stable climates, of epochs when life flourished in abundance. Beneath tropical skies, you can read the changing climate conditions and the transition zones between rock layers. Where the red sandstone gives way to limestone, there is often a thin band of different material, perhaps a layer rich in volcanic ash from some ancient eruption, or a stratum of unusual minerals that formed during a period of dramatic environmental change. These boundary layers are like chapter breaks in Earth's story, marking moments when one climate regime ended and another began. The limestone layer itself contains its own internal chronology. Closer examination reveals subtle variations in color and texture that correspond to cycles within the ancient climate system. Darker bands may represent periods when the ocean was less oxygenated, perhaps due to changes in circulation patterns or atmospheric composition. Lighter bands might indicate times of increased marine productivity, when abundant life in the seas left behind more calcium carbonate deposits. Above the limestone lies a layer that tells of dramatic change. A band of shale formed from fine clay particles that accumulated in quieter, deeper waters. This layer represents a time when sea levels rose dramatically, perhaps due to melting ice caps or thermal expansion of warming oceans. The fine-grained nature of shale indicates that the ancient sea was deep enough and calm enough for the smallest particles to settle undisturbed to the bottom. Embedded within the shale are traces of organic matter, the compressed remains of ancient plant and animal life that lived and died in those long-ago seas. These organic traces carry chemical signatures that reveal the composition of ancient atmospheres. Scientists can extract and analyze these microscopic fossils to determine carbon dioxide levels, oxygen concentrations, and even temperature ranges. From millions of years ago, the next layer upward marks another dramatic shift in Earth's climate story. Here the fine shale gives way to a coarser sandstone, indicating a return to more energetic depositional environments. This transition might represent a period when sea levels dropped, when rivers and streams once again dominated the landscape, carrying larger particles of sand and gravel from distant mountains to create the deposits that would become this rock layer. Within this newer sandstone layer, you can see evidence of the ancient river systems that carved across this landscape. Cross-bedding patterns in the rock show the direction these rivers flowed, preserved as diagonal layers that were once the sloping faces of sandbars and riverbanks. The size of the sand grains tells you about the energy of those ancient waters. Coarser grains indicate faster flowing rivers, while finer particles suggest more gentle, meandering streams. Some layers contain unexpected treasures, the fossilized remains of plants and animals that lived in these ancient environments. A piece of petrified wood embedded in the sandstone might be the trunk of a tree that grew along the banks of a river that disappeared millions of years ago. Leaf impressions preserved in fine-grained rock layers can reveal what kinds of forests grew here, what the rainfall patterns were like, and how warm or cool the climate was during different epochs. The preservation of these organic materials required very specific conditions. For a leaf to be fossilized, it had to be buried quickly by sediment, protected from decay by the chemistry of the surrounding environment, and then slowly replaced by minerals over vast periods of time. Each fossil represents not just a single organism, but an entire ecosystem, the climate conditions, the soil chemistry, The seasonal patterns that made life possible in that ancient world dot. As you continue examining the rock face, you notice that some layers contain evidence of more dramatic climate events. A thin band of unusual rock might represent the aftermath of a massive volcanic eruption, when ash and debris in the atmosphere altered global climate patterns for years or decades. Layers with unusual mineral compositions might indicate periods when the ocean chemistry changed dramatically, perhaps due to shifts in atmospheric composition or changes in the global circulation of ocean currents. The thickness of different layers also tells important parts of the climate story. Thick layers indicate long periods of stable conditions, when the same type of depositional environment persisted for millions of